All right, I want to welcome everybody to the virtual seminar today titled The Role of Water Activity and pH in Food Safety. I am the presenter, Brady Carter. I'm a research scientist for Decagon Devices, working in the areas of moisture relations and moisture interactions in foods. Um, my area of expertise is in measurement of water activity and moisture absorption isotherms. And today, what I want to talk about is how water activity interacts with pH to give even a higher level of food safety, and how these two measurements, in some cases, may be the two most important measurements you make on your food product in terms of food safety. And so that's what I hope to be able to explain today. So let's get into it. Okay, so when it comes to microbial stability, is it water activity that gives you the control and the safety? Is it pH that gives you the control or the safety? Or is it both? And are they working together? And as we're going to discuss today, we're going to find out why water activity, why it may be a candidate for providing microbial stability, why pH may be a candidate for providing microbial stability, but then ultimately them working together is what gives you the greatest level of protection against microbial growth. And the talk today is going to be very focused on microbial stability. When we talk about water activity and pH, that's really what we're emphasizing. How you can use these measurements or these tools to make sure that your product remains safe from microbial contamination. Okay, so starting out, let's talk first about water activity. What is water activity? Well, water activity is a measure of the energy status of water in a system. This is derived from fundamental thermodynamics, where we can find from the first law of thermodynamics, we can derive an equation called the Gibbs free energy equation. And that equation provides the information about the energy potential or chemical potential energy of any kind of a species. In this case, we're talking about water. And what we learned from that equation is that if we want to know something about the activity of a species, then we need to know something about how readily it escapes into the vapor phase. And so we write this definition, as you see in the middle of the screen, that water activity is equal to this F over F naught value. That's the fugacity or the escaping tendency of a material. And ultimately, that is what provides the information about, going back to Gibbs free energy equation, the energy of the species, or in this case, water. So from that equation, we find out that the energy is directly related to the water activity, which is then directly related to the escaping tendency of a material. So if we want to know something about the energy of water in a product, we need to know how readily can the water escape out of that sample into the vapor phase. And under most conditions, we can do that by looking at vapor pressures. And so this P over P naught value that you see as the rest of the equation is the partial pressure over a sample, or vapor pressure of water above a sample at a certain temperature, and then that's divided by the saturated vapor pressure, or the vapor pressure of pure water at the same temperature. And so that's the way, from a practical standpoint, that we can determine water activity. It's the partial pressure divided by the saturated vapor pressure. So if we want to know something about the energy of a material, we can take that material, put it inside of a closed container, allow it to water to vaporize out of that sample into the headspace above it, creating a pressure or exerting some pressure, that if we can measure that pressure and that partial pressure, and then take that and divide it by what the pressure would be if we were measuring pure water, then we can get this value called water activity. Obviously, if that vapor pressure of water above a sample is the same as the vapor pressure of pure water, then this value becomes 1. And so water activity of pure water is 1. And then it becomes a ratio or a scale. As that vapor pressure reduces lower than what you would get if you had pure water, then so does the water activity. And so it's a scale from, in theory, 0 being completely bone dry, no water, up to 1, the water activity of pure water. And as you reduce the energy of that water by having it interact with different things in the product, that will lower the vapor pressure above the sample and hence will lower the water activity. Now, water activity is also related to relative humidity. Relative humidity of the air is measured in the same way. It's the vapor pressure in the air of water divided by the saturated vapor pressure at that temperature. It's the same way that we measure relative humidity. So if you were to measure relative humidity inside of a sealed chamber under equilibrium conditions, then that relative humidity divided by 100 would be the same thing as water activity. They're essentially the same thing if you're in a state of equilibrium. And that's important because the environment, then your relative humidity, your ambient relative humidity, can impact the water activity of your sample because they're related. And water moves from high energy to low energy, high water activity to low water activity, or high room relative humidity to low product water activity, or vice versa. High water activity of a product water will move and go into an environment who has a low humidity. And so from all this, we now have this definition that we started out with, that water activity is ultimately a measure of the energy status of water in a system. How much energy does that water have in comparison to pure water? And so we stay away from the terms free and bound. These were old definitions or are common definitions that are associated with water activity. But unfortunately, these terms have no scientific meaning, free and bound. They mean different things to different people. And so we try to stay away from those terms. They have some usefulness if they're used in the right connotation, because in fact, as water becomes more chemically bound in a product, its energy will be reduced, and so its water activity will be reduced. And that water is no longer available for other processes to happen, like microbial growth. But it is not true that at a water activity of 0.5, it is not correct to say that 50% of the water is free and 50% is bound, because this isn't a quantitative measure, it's a qualitative measure. It is correct to say at 0.5 water activity that that water in that system has 50% of the energy that pure water would have. Okay, so here's an illustration. If we had some sort of a product inside of a sealed chamber, be it a pharmaceutical product, a food product, and we allowed that sample in the sealed container to come to vapor equilibrium, so water vapor is escaping out of the sample, and at a certain point there will be no net change in the number of water molecules that is in the headspace above the sample, and we call that equilibrium or steady state. That doesn't mean that a water molecule just stays up there and hangs out. Water molecules are constantly changing their energy state, but as one goes into the vapor state, another one goes back down into the sample, and so there's no net change in the number of water molecules over time. And at that point, it will exert a certain pressure. This is what we called the partial pressure. If in a different container we put water in that container and allowed it to come to equilibrium, there will likewise be a certain number of water molecules that have enough energy escape into the vapor phase and exert a pressure. And the pressure that's exerted we call the partial pressure, or the saturated vapor pressure, or the vapor pressure of pure water. Well, it ends up that the vapor pressure of water can be determined simply by temperature. Temperature is what dictates how many water molecules will be in the headspace. And so if we know temperature of the sample, we can calculate that saturated vapor pressure. And if we know, then all we need to measure is the vapor pressure inside of the chamber with our sample, or the partial pressure. And it ends up that we can actually do that in a direct or primary way simply by measuring what the dew point temperature is of that headspace. The vapor pressure dictates the dew point temperature. So by knowing the dew point temperature of the conditions where there's the sample and the sample's temperature, we can know both the partial pressure and the saturated vapor pressure, put them together, and you have water activity. And that's exactly how our chilled mirror system for measuring water activity works. This is the picture you see is the instrument called the Aqualab Series 4TE. This is a primary method for measuring vapor pressure. It's not related to any kind of sensor, humidity sensor. It's a direct measurement of the vapor pressure of the headspace above the sample in the chamber, as determined by the dew point temperature of the conditions in the chamber. And so the way that we figure out what that dew point temperature is that there's a mirror inside of the chamber, as you can see illustrated in the model below. That there's a mirror in there, and we control the temperature of that mirror very tightly, and we cool the mirror down until the point at which dew forms, and the optical sensor senses the point at which dew forms on the mirror. And by knowing the temperature of the mirror at that time, then we get the dew point temperature of the conditions inside the chamber, and from that dew point temperature we then know what the partial pressure is inside of the chamber. Then by using an infrared sensor to measure the sample's temperature, by knowing the sample's temperature, we can calculate the saturated vapor pressure just by knowing what that sample temperature is. Now we have the two values we need in order to have water activity. And so because this is a primary way of measuring water activity, it's the highest, most accurate way. It's a very fast measurement, less than 5 minutes. There's no need for equilibration to a sensor, an RH sensor inside the chamber. So that makes it very fast. It can measure the entire water activity range, and it's very reliable. The only downside is that you have to keep it clean. The mirror and the infrared sensor do have to be maintained and kept clean in order to get accurate readings. If there's anything on those, they will impact the ability to measure the temperature correctly, which will then cause a reading to be off. So let's summarize by differentiating water activity from another common moisture measurement called moisture content. And in a lot of cases, moisture content will be more easily understood or more commonly understood than will be water activity. But moisture content is a quantitative measure of how much water is present, as compared to water activity being a qualitative measure of the energy status of water in the system. So while moisture content tells you how much water is present, it doesn't tell you what the water is actually doing or what its energy is. That comes from water activity. And it ends up that microorganisms only care whether or not they can access the water. They don't care how much water is present. And so if we take a look at the mode of action of water activity in terms of controlling microbial growth, what happens is that you have a microorganism that's surrounded by a semi-permeable membrane, and inside of that microorganism, its conditions of the organism will have a certain water activity controlled internally. And it needs to be able to access water from its environment in order for it to be able to replicate and grow. If it encounters conditions where the water activity is lower than the conditions inside of the organism, then water wants to move out of the organism instead of into the organism, and we call that osmotic stress. And as water preferentially moves out to the lower water activities, that causes a loss in turgor pressure by the organism and causes it to not be able to replicate or go through its metabolic processes that are required. And so it essentially has to stop. It has to go into a dormancy stage. Now, each organism has a unique ability to be able to respond to these osmotic stress conditions. And so they have the ability to be able to concentrate solutes in their interior. Typically these are amino acids, polyols, sugars. They may be able to produce them themselves. They may get them from the environment. But the point is to concentrate those inside the organism in an attempt to bind up water chemically and lower the water activity. Trying to get that water activity to be lower than the water activity of its environment, so that water will now again start moving into the organism so that it can access it and use it for its to reproduce and to grow. But each organism has its own unique ability to adapt to these conditions. And that's why each organism has a very specific water activity at which they will stop growing. And that's dependent upon its ability to be able to react. And so we can actually identify these water activities, minimum growth levels for water activity for each of the different types of organisms. As long as you can maintain your environment of the product at water activity values less than their growth limit, then you prevent the replication and growth of that microorganism, and it keeps your product safe. While it's sitting in storage, it's not going to replicate and grow to high enough levels to cause an infection. Now, water activity lowering is not a kill step. It doesn't kill off these organisms when they encounter osmotic stress, although over time their numbers will reduce. But it does prevent them from replicating and growing. So it's a prevention of growth, not a kill step. It has to be combined with good manufacturing practices and a kill step in order to have removed the organisms or enough organisms to prevent an infection to then have its efficacy in preventing growth from that point on. And so we can take a look at a chart that shows us where these minimum growth limits are. In this case, this is for pathogenic bacteria. Notice that the lowest that they can grow at, and this is for Staph aureus under aerobic conditions, can grow down to water activities as low as 0.86. the other organisms stop at various water activities. Again, this is reflecting their individual capabilities or abilities to be able to react to osmotic stress and be able to change their internal water activity. Also notice at the bottom that these are the minimum growth levels, with all other conditions being optimal for the growth of the organism, meaning that it's at the optimal pH, temperature, and etc. And that's key, the pH. So these are representing where these organisms are going to stop growing if the only thing that's being controlled or changed is water activity. So these represent worst case scenarios. We're going to see if you combine the impact of water activity with the impact of pH, that at higher water activities you can actually stop growth if it's combined with the impacts of other factors. Now if we move on to the molds, common spoilage molds, notice here that the growth stops at about 0.7, except for a xerophilic mold that will grow down to as low as 0.61, although not a common spoilage organism. So this is why we typically call the practical limit for microbial growth at 0.7 water activity, because below 0.7, now all organisms stop growing at 0.6, but the only organisms that will grow between 0.7 and 0.6 are some very few xerophilic molds and osmophilic yeasts. So again, you can use this water activity. If you get it low enough, you can prevent mold spores from being able to replicate and grow and cause your product to become moldy. How about for yeast? Again, there is an osmophilic yeast that will grow in water activities less than 0.7, but for the most part, the yeast growth is going to be stopped at 0.80. So what can you use water activity for? You can use it to prevent the growth of bad bugs or bad organisms that are going to spoil your product and cause it to be unacceptable, or even to cause sickness in the consumers. So it's an excellent tool for assuring the safety of a product, and becomes a tool for as a verification of critical control points for HACCP's plans. So by measuring water activity, you have a record of evidence that your a critical control point of dehydration or lowering water activity is being used effectively. So that's the way you verify it, is through measurement of water activity. But water activity can also be used as a great way of ensuring consistency of the product. If the water activity is always the same, then you know that your processing is remaining the same. So it's a good way to know that you have consistency, and a good way to know when the end of processing has occurred, where you've lowered the water activity low enough that you can now stop. There's no need to further dry the product or further subject the product to heat, and so that can be a savings in terms of energy and time, which are critically important when making or manufacturing food products or any kind of manufactured product. Okay, let's now move on to pH then. What is pH? Well, pH is a measure of the relative acidity or basicity of a product. How acidic is it? How basic is it? And so it works on a scale that has 7, the value of a pH of 7 as neutral. And this would be what you would get if you had distilled water. And so it's based upon distilled water being the neutral point, and if you go higher than 7, then you're considered basic. If you have a pH that's lower than 7, then you're considered acidic. And so you can see here a breakdown of different types of products and where they fall in terms of their pH level. You start getting into fruit juices, then high levels of citric acid causes them to be acidic. So they have quite lower pH levels, and of course associated with the lower pH is that sour and tart flavor that you would associate with something like a lemon. And then you have things that are basic as well, things like baking soda, bleach, that are very highly basic materials. Not a lot of foods fall under the basic category. That tends to have a soapy taste to it, not something that's really desirable. So foods tend to either be neutral or they tend to be acidic. And so this scale really it's based upon a set of standards of different levels in comparison to distilled water being at a pH of 7. And ultimately, the way that you calculate the pH value is it's the log value of the formation of H3O molecules because of the dissociation of hydrogen from acidic materials or hydroxide from basic materials. So how do you measure pH then? There are a couple of different ways that you can measure it. One is through visual. This is through an indication paper where it basically is linking up a color change that you can then put next to a chart, and based upon the color of the strip, identify an estimation of what pH level you're at. So this is a very rough way of doing it, but obviously very inexpensive and the least expensive way of being able to do that, and a very fast way of being able to get an idea of what the pH is. For more higher level of accuracy, you would go to a photometric method using a spectrophotometer, or probably the most common way of measuring pH is through a potentiometric method, or where you take electrochemical measurement of the conditions using a probe that has to be maintained and kept damp. You store it in a buffer, typically a neutral buffer, until the point at which you're going to take a measurement, and then based upon that change in the electrical chemical properties, you can relate that then to, or calibrate that to, a pH scale. Again, using water as the standard, as a pH of 7. And then there's also something called titratable acidity, where you figure out how much sodium hydroxide you need to neutralize, and based upon how much is required, that's called the titratable acid level. And it ends up, this is actually the best indicator of microbial stability, because it actually gives a direct measurement of the level of acidity, or the amount of acid present in the product, as opposed to pH being just an electrical chemical measurement, but not as commonly used in looking at pH as a pH probe would be. Okay, how about pH growth limits then? We can create a chart similar to what we saw with water activity, where we can establish minimum levels for growth for different types of organisms, but in this case we're talking about pH instead of water activity. And you'll notice that that there are quite a few that tend to want, well, pretty much all of the organisms prefer a neutral pH for their optimum growth, but they can grow to more acidic pH values, most of them stopping at around 5, a pH of 5. Some can go a little bit lower, as low as 4.6 down to 4.4, and then the one that tends to be problematic are the ones that can get down to 4.2. And that's one of the reasons why portions of the food code were changed to reflect this. It used to be that pH of 4.6 was considered to be a limit, but now we know that there are many organisms that can grow down to as low as 4.2, and so now the lower limit for pH to have control of all types of organisms is a pH of 4.2. So what are the uses for pH adjustment, or having a acidic pH or a basic pH? And again, this comes down to it being an effective way to prevent or preserve foods and prevent the growth of microorganisms. And so this is most commonly known as pickling a material or a product by either inducing the production of lactic acid through microbial action, or through enzymatic reactions, or by the direct addition of an acid. Typically this is done through the addition of vinegar, which is a common source of making things to a lower pH. Another reason, so that would be one reason to adjust it. Another is to adjust the flavor, to increase tartness, or you would lower the pH, or to decrease the level of tartness, you might increase the pH. There are lots of chemical reactions that are pH dependent, so they have an optimal pH level for that reaction to occur. And if the pH, if it's too acidic or too basic, then that can prevent the chemical reaction from proceeding. And then again, like with water activity, if pH, if a product is acidic, and that's the way, or that's the the critical control point is that the product is acidic to prevent growth, then the way to verify that, or the tool to use then, would be pH measurement. And then you would want to keep a record of the pH measurement values that you obtain for a food product. Okay, so then how do water activity and pH come together? At the first we asked the question, is it water activity? Well, we've shown that yes, water activity can control the growth and there are minimum growth limits. Is it the pH? Well, we've shown that that's also true. There are minimum growth limits for microorganisms based upon pH. But if we combine these effects, we can actually get more effective control of microorganisms, and that's something we call hurdle technology. And so the idea here is that there are different things that will impact growth of organisms and their ability to be able to grow. And you can see these symbols over to the side. So there's everything from heating, temperature that you're storing it at, water activity, pH, redox potential, having preservatives present, having competitive organisms, how many vitamins are available, and whether there's a good nutrient source. And all of these combine together and have to be optimal for a microorganism to grow. And so by changing any of them, you have the potential to create a situation where you can prevent that growth. And so what we see in this image is different situations where at times you've had control of growth and other times you don't. For instance, in number 3, temperature we weren't refrigerating it, so temperature alone wasn't an effective control. But if you combine that and then you put water activity in front of it, the water activity would be low enough in this case to prevent the growth of the organism. It's a big enough hurdle to prevent it from moving any further. But in the case of number 6, let's say that water activity alone is not, but if you combine its impact with pH as well, by the time the organism tries to get past the water activity, it can no longer get past the pH. You've created enough hurdles in its way to prevent it from growing. In some cases, you have to go to a preservative to be able to get the prevention. Or in number 4, even that wasn't enough. You'd have to try and go back and change your temperature hurdle and increase it by refrigeration to prevent the growth. So it's a matter of combining these all to be able to get an effective control. We can define these hurdle effects. Sometimes you might have the agent alone. Sometimes you have a additive effect where you get the effect of both A and B hurdle, and so it's a combined effect of those. Sometimes you get synergism though, where the combined effect is actually greater than the sum of the two effects themselves. Sometimes you may have one that impacts the effect of the others by being present, so you have antagonism where they aren't quite as effective as they would be had they been there by themselves, or at least what the summation of their combined effects is. And so each of these different types of combinations can be happening. In the case of pH and water activity, actually what we see is a synergistic effect, such that you can, by combining the effects of the two, you can have effective control at levels that would typically be considered unsafe for either pH or for water activity. And what this results in is the formation of these interaction tables. This is taken directly from the 2005 Food Code, but still remains viable. If you look up the definition in the Food Code today of potentially hazardous foods, you will see these tables that are used to determine whether a food is potentially hazardous. So PHF means potentially hazardous. That means that food has the potential to support the growth of dangerous microorganisms that could cause foodborne illnesses. PA means that you need a product assessment, which means that you either have to, for those products, for the products that have water activities and pH values that fall under the cell that shows PA, you would either have to have time temperature control for that product, or you have to prove that you have a preservative system that is going to be effective at preventing growth. But these tables, there's two tables. Table A is what I'm showing now, and you'll see Table B. Table A is specifically for a product that has had a kill step and then is subsequently packaged to prevent further contamination. And with these types of products, you can actually move them to quite high water activity and pH and still have effective growth because you've eliminated everything except spore-forming organisms. And so it ends up that at a 0.92 water activity, you can be considered safe under these types of conditions, or at a pH of 4.6 or greater. And again, that's because you're only dealing with spore-forming organisms. But you can also get effective control at even higher water activities as long as your pH is lower. So while you may not be safe at a water activity of 0.92 to 95 at 4.6 or sorry at 5.6 pH or higher, you are still safe at 4.6 to 5.6. So you have these combined synergistic effects that give controls at even higher levels. And if we move to table B, which is a more strict or stringent table, this is for a situation where you don't have a kill step, or you have a kill step, but then you don't immediately package the product. And so for these situations, you have to maintain a water activity less than 0.88 in order to be considered safe, or less than 4.2 to be considered safe. But you can have higher values of both. You can be above 4.2 and above 0.88 and still be considered safe if you have the combined effects of both. So 4.2 is at any water activity, 0.88 is at any pH. But then you see where you take the table, you find your water activity, you find your pH, you see where the table connects, and if that in that cell or that square it says non-PHF, then you're good to go. You don't have to store your product under time and temperature control. But if you fall under one that says PA, then that means your product could be hazardous, and you have to either do time temperature control or be able to prove that your product cannot support microbial growth. So now let's take just a quick survey of the water activity and pH of different types of foods. So if we look at something like a strawberry preserve, it has a very high water activity, lots of water, some sugar, so you do have a little bit lower water activity. But look at the pH. The pH is quite low enough to prevent growth, even though the water activity is high. Lots of citric acid present. You also have mustard, has a very low pH but high water activity, and you can see as you go down this chart, there's lots of high water activities here, but low pHs. These products are safe and are being maintained safe because of their pH, not because of their water activity. If we move on down, now we get to lower water activities but higher pH levels, where something like maple syrup is high in sugar, so it's lower water activity, but its pH is fairly neutral. So in this case, it's the water activity that would provide the safety, not the pH. Or something like the hazelnut spread you see, quite low water activity, but its pH is neutral. So if we plot those, there really isn't any kind of direct relationship between water activity and pH. You can have foods that have very high water activity but have low pH. You can have foods that have medium water activities but low pH, or medium water activities and high pH. There's really no direct correlation. Now, as you add acid to a product to lower its pH, it does also have some impact on water activity, because acidic materials tend to be polar, and so they do like to interact with water and will have a lowering of water activity. But essentially there's no great direct relationship that as you lower the pH, you lower the water activity. And so we come to a question with some of these types of products of whether or not you would need to refrigerate them. Something like mayonnaise, which has a water activity of 0.93, very high water activity. Its top ingredients are oil, water, and egg. Do you have to refrigerate this product? Well, its pH is 4.1. It has a lot of vinegar in it as well. So you would not need to refrigerate this product at all. In terms of microbial safety, it's never going to support microbial growth. Now, if you don't refrigerate it, because it's so high in oil content, it is going to be very susceptible to going rancid or experiencing lipid oxidation. So the reason that you would refrigerate, or most people do refrigerate mayonnaise, is because you want to prevent it from having lipid oxidation or going rancid. And that's its main purpose in refrigerating, not to keep it safe from a microbial standpoint. It's to be able to keep it fresh and keep it from having lipid oxidation. How about grape jelly? Grape jelly has both a low water activity and a low pH. Top ingredients: grapes, corn syrup, very high in sugar. Do you have to refrigerate this before opening? No. But if we open grape jelly, most of us are going to naturally put it in the refrigerator. Again, it's not because we have any concerns or there's any concerns in it for microbial spoilage. It will not support microbial growth of pathogenic bacteria. It will mold, but it will not. Well, even mold will be fairly limited here because it doesn't like the pH. that's so low at 3.1. So this product is microbial stable, but it's, again, we consider when we just by consumer preference, we expect that to be nice and cool when we use grape jelly on a product, and so we tend to keep it in the refrigerator. But again, these are the reasons are for product quality in this case and not for microbial safety. There are types of products obviously that we refrigerate because if you didn't refrigerate them, they would very quickly develop microbial growth and would spoil. And if you then ate them at that point, you would be susceptible to pathogenic bacteria that could lead to foodborne illnesses. Okay, so then how do we control water activity? Well, the best or most common way of controlling water activity is to dry a product. Dehydration will lower the water activity. As you remove water from a product, it will cause its water activity to go down. And the relationship between the amount of water present and the level of water activity or energy of water is called a moisture absorption isotherm. And these are unique to each type of product. So the amount of water that you remove isn't going to result in the same water activity in two different products. So that has to be well understood for your particular product to know how that drying process can be optimized. Another way to lower water activity is to add humectants. Humectants are materials that lower water activity. Some of the most common are sugar, things like high fructose corn syrup. Salt is a very effective humectant, lowers water activity. It's why from ancient times we've salt infused foods to make them more stable. Leads to things like soy sauce that are very high in salt content. You have things like sorbitol, maltodextrin, and even starch lowers water activity. It's not very effective at lowering water activity, but anything that has polar portions to it or is polar, put into a material is going to impact the water activity and will lower it. Now, there are limitations to adding these ingredients to lower water activity. One of those is solubility. Most of these have a solubility limit to where if you add any more, they'll come in solid form and start to crystallize and will not be desirable in a food product. Another limit is molecular weight. The lower the molecular weight, the more effective a product is at lowering water activity. So if you try to add something big like starch, you have to add a whole lot more of that material in order to get an effective lowering of water activity. Another problem is that humectants being added have organoleptic consequences. So they could change the flavor, obviously. You put more sugar in, it's going to be sweet. If you put more salt in, it's going to taste salty. Um, Glycerin is a very commonly used humectant. It's very effective at lowering water activity. Another advantage is it's very neutral in terms of flavor. At high levels, it can actually result in a metallic flavor, but it also has it's completely miscible in water. Crystallization during storage, you have a high sugar content, it may be okay, but then if it experiences any kind of drying, lowering of water activity, you get below its solubility limit because of lowering water activity, and now you start to have crystallization. If you add reducing sugars to products that are high in protein or have protein, you then suddenly make them susceptible to browning reactions or other types of reactions. And then sometimes at high levels, these humectants can bring in a toxicity, something like a propylene glycol. You may ask then, if you want to lower your water activity by the addition of a humectant, you're going to put some glycerin or glycerol into your product to lower the water activity. How much do you need to add? There are actually tools that can be used to figure out how much you need to add to lower the water activity. This is a screenshot from a software program that we provide from Decagon. This available for purchase. It's a toolkit that includes lots of different tools, models to be able to use in terms of water activity to figure out and do food engineering on your product. But this is one of those tools. It'll allow you to set your current water activity. In this case, it's set to 8.23. You want to lower it to 0.7. You have 7.6 grams of water, and then you can choose a humectant, in this case glycerol. You hit calculate, and it will tell you that you would need to add 5.9 grams of glycerol to this product that has 7.6 grams of water in order to get the water activity to lower from 0.82 to 0.7. And again, this is a prediction. It's not going to be completely accurate every time, but it is powerful in the sense that it gives you a good starting point. And of course, this can be scaled up to much larger scale for large batch values to know how much you would need to add in order to be able to achieve the desired change in water activity to make a product that may be susceptible to microbial growth to lower its water activity to a value that could be now considered safe. And we've done experiments on this to see how effective the prediction is. So this is a syrup sample that we added glycerin to at different levels. And then based upon the levels that we added using the tool that I just showed you, we could predict the water activity using the tool. And then we actually made the combination and measured the water activity using one of our Aqualab instruments. And you can see that the prediction is surprisingly good at being able to predict the water activity that's going to the actual product itself is going to have. The more ingredients, the more complex the product. Obviously, the less accurate this prediction is going to be. But again, it's a very effective tool at getting you an idea of how much of a humectant you would need to add to your product in order to get an effective water activity change. How do you control pH? One of the ways is you can directly add acid to your product. Typically, this is done by acetic or acid, which is vinegar, lactic acid, or citric acid through fruit juice. Common foods that this method is used is something like a pickled fish or pickled vegetables, where you add vinegar to them and then let them take in the vinegar that pickles them and then makes them to a lower water activity. Sometimes it's through the addition of naturally acidic foods like tomatoes in spaghetti sauce. The addition of the tomatoes lowers the pH of that entire sauce just by simply adding tomatoes, plus it adds the flavor and texture you would expect. Another common way to control pH or lower pH in most cases is through fermentation. This could be lactic acid formation by bacteria that are preferentially have growth, and by their growth they produce lactic acid, which then lowers the pH of the product and then prevents any growth of other types of organisms because they are now existing in a very low pH environment. And examples of this would be pickles, sauerkraut, fermented sausages, olives, and other types of products. Okay, so in conclusion, water activity and pH are sort of measurements that really kind of go together. You could effectively set up a HACCP plan for a product using water activity and lowering water activity and pH level as your control points or your critical control points, and then have a water activity meter and a pH meter sitting there in your laboratory, and then you take a measurement on your foods routinely. What is its water activity? What is its pH? Are you falling into the right square on your matrix from the tables that I showed you earlier from the food code? As long as you're continuing to fall into those correct values, you set those as your specifications. You verify that routinely, and you're making sure that your product is safe. So these can be effectively used alone, but they are even more effective used together, and can be used as an effective way to be able to determine whether or not your product's safe. And then there are ways that you can manipulate both of these things, water activity and pH. We talked about some ways that can be done, and manipulate them to get to levels that are going to be keeping the product safe. At Decagon, we have actually available both water activity instruments and pH meters that you can purchase from us to combine them into an effective tool. And we're continuing to work even on additional systems that will even make that and facilitate that to make it even easier to collect your data through a system that we now provide called Reflex that actually allows for the collection of digital records, can collect both water activity and pH values into a common interface, which then makes a digital record of those values that can then immediately be used as part of your record keeping for your HACCP plan with no writing down any kind of values. You hook up your water activity meter, you hook up your pH meter, both of which again can be purchased from us, to this Reflex system. It sends the data to your computer wherever you are and warns you whether or not there are you have values that are falling out of specification. So if you're interested in that, I would encourage you to contact us, and we can provide you with some additional information. And here is my contact information. My role here is to provide scientific support for anyone who might need it. So feel free to contact me by phone or email if you have questions specific to your product or situation, and I'd be happy to discuss those with you.